Hey there. Last June, there is Slonser blog post that made a big noise in the bug bounty universe because it was pushing the barriers in what was possible in terms of bug bounty. It was putting self-XSS back into the scope where most of the programs on the bug bounty platforms were putting them out of scope. How was it possible? The blog posts go through different ways, and some of them are original and based on experimental features from the different modern browsers and can leverage some new vectors for exploitation program. And so Slonser present first what could be a solution for that. The key challenge for these vulnerabilities are usually executing the XSS payload, and for that we need to log in as the attackers because it's a self-XSS and therefore everything is executed from our profile. But because we are logged into the attacker's account, the attack is missing the purpose because we are on attacker sessions and therefore cannot really exfiltrate or exploit the victim that will be running that script. For these cases, usually you have either tinkering, fuzzing, or you just go back to the documentation at what he did by reading the RFC. And one of those interesting items were the credentialless iframe. And those credentialless iframe are context that you can load within the page, but doesn't share the same context as the others, which means we have side by side two iframe to the victim domain. One of them is credentialless and one of them is the normal. And what you can see is that the one on the right is logged in as a victim, but the one on the left, which is credentialless, is not logged in at all, as if you were running the page as another session. The thing is, those two frames are separated a different context and sandbox per itself. The one on the left doesn't have access to the victim. However, because it can be framed, we can leverage the setup. That leads us to our first lab, which is the credentialless same origin issue. Now, we can imagine something like having two iframes, and one of them being credentialless and the second one being the login one. And the XSS itself could just be leveraging the framing and relying on the Windows stop. And because we are relying on the Windows stop, we are able to bridge between the same origin frame. And because they have technically the same origin, that XSS can interact with that frame. So the first lab consists of two iframes. One of them is credentialless, as I said, and the second one is the normal one, so the victim. And the XSS is just showing the cookies from the second frame. So after 1 second, we alert from that frame the cookies of that frame. If we are loading it after 1 second, we have lol how you accessed me, which is the cookie that is set by localhost 8082. That's the backend service for the 8082. As you can see, the XSS is the Windows Top 1 alert for the Windows 1 document cookie, and the server on root is setting the cookie itself, which is setting up our lab. Next comes a more real example of what you can encounter when you're doing bug bounty. You could have self-XSS in the profile or the welcome page or the landing page, but you are also able to CSRF into the login, which is something you look for when you have a self-XSS. And so the idea here is to leverage that CSRF login in order to also use the credential-less frame. What would be the attack vector for this case? We have our attacker site, which will have set up two iframes, one with the victim account already logged in, And another one, which will be the credentialless iframe, where we would be setting up the attacker session with the self-XSS. And because of the CSRF login, we can actually do that directly in the credentialless iframe. So here it's set up for logging in directly on the credentialless iframe. And that one is executing after a set amount of time, kind of the same thing we did on the previous one. However, we will grab the cookies of the victim, but also the ad cookies. So let's take it to our lab 2. So for that, we will be running the exploit. The exploit itself is going to set up two iframe, one of them being the CSRF in credentialless. We'll be logging into localhost 3001 as attacker. So I have set hard-coded credentials and session IDs that will be set to cookies. The login itself is accepting a username and a password. And when I'm posting it, I'm generating a session ID, which I set as a cookie and redirecting then to the home. And for that specific case here, the home itself is going to run eval on the window name. And what's going to happen is that the frame on the left will be replaced by edited by char1. Our cookie is the cookie of the attacker, and the victim cookie will be the second frame document cookie. So technically, we should see two different cookies, the attacker cookie and the victim cookie. Go here, select logged in. Our cookie being 8A is the cookie that is on the attacker side, and the victim cookie has been set here, and those are living together thanks to the Windows top bridge that we created. Now, Slonser is also explaining that there are some cases in real world that would not be as simple as just log in, and will include CAPTCHA here. It's mostly one interpretation of what can happen, and he is setting up some kind of WebSocket server where in his scenario, the attacker will resolve or solve the challenge beforehand and provide the token so that the CSRF can actually go ahead and log in correctly the session. The attack will go as the victim is clicking the link itself, the CSRF or the exploit is running, and it will prompt the attacker to give the right token for the CAPTCHA and then follow on the attack as we saw on the previous lab. So what it does here is just adding an additional CAPTCHA token layer, which he is simplifying by having a WebSocket server that is prompting the attacker, and the attacker would just provide the token. But I didn't really want to have this manual entry, so I also simplified it in my way. The flow itself is going to automatically request a token, and here I'm like waiting 5 seconds and then generating a token randomly. But you can imagine having some kind of AI running in the background and solving a challenge or CAPTCHA challenge for you, and then providing the right token so that you can send it for the flow to continue and carry on. Except that different step, that's basically the same exploit that is running. So we have the same setup for the iframes. We have the name, setting up the content to display the two cookies, calling the CSRF HTML page, and then logging also on the right side. We have the server that is the same, but it now also requires on the login a CAPTCHA token, and this CAPTCHA token, for the sake of simplicity, just require it to be whatever. It just need to not be empty. So as long as it's not empty, it works. So for this to work, I have now a backend which is going to be emulating the victim site, the attacker, which will be serving our exploit.html, and our WebSocket server, which will be also running our attacker side, but that will be solving the challenge for us and keeping track of things in real time. So if I Docker compose up the whole thing and up the page, log in as a victim, it's going to submit the CSRF. Now the self-XSS is running. It's going to be executing, and beam, we have the session ID of the attacker and also the session ID of the victim, which means that we can now, thanks to the self-XSS, execute JavaScript on the session ID of the victim. For the sake of visualization, we can see that the WebSocket received the connection request and it generated a CAPTCHA token and then sent it to the server, which then used it to log in. So everything is working as expected. This is, however, not what you will find in real world. One thing he's mentioning here is the clickjacking, which I didn't create any labs because I found his scenario not realistic and won't fly into a bug bounty context or environment. He would social engineer the victim in order to believe that he has registered into a new website, and then using clickjacking, it will send emails, credentials that will be the attacker credentials, but on the victim domain, and passing those as the new product credentials. But in the end, it will be clickjacking and overlaying the victim domain to do the attacker session connection, which for me isn't really working, which leads us to the iframe options deny, which is what you would find mostly on real world. And so for those cases, you have to be a bit more creative. And for that, he's suggesting the use of a new experimental API, which is FetchLater. And FetchLater is an API that's for differing fetches requests, and they can be sent after a specific time or at a specific scheduled time. And therefore, it's interesting because you would be able to log in like as a new tab with the self-XSS, like as an attacker. We still need the CSRF login, but you would be registering the FetchLater's request, and after that, you would be logging out from the attacker and expect the victim to log in at a later date. And because you would have registered the FetchLater request, those will still be running in the background request. They will be running with a new session context that will be under the victim context. In his example, he's using change rights to a privilege escalation of some sort, but you could also run some exfiltration on the later date and from there do some ATOs. So for this specifically, I have created some Docker Compose, which is going to set up a reverse proxy because FetchLater requires HTTPS URLs, and therefore we will have the victim, which will be the app. We will have the WebSocket, which will be there to keep track of things that are happening in the background, but also to solve the CAPTCHA. And the caddy will be serving the exploit page. We have the backend, which is a bit more complex, but in a sense will still be the same. We do some logging and keeping track of things in the WebSocket. We have some cores. We have the same login and password for simplification. And because I didn't want to embed the XSS every time, I have chosen to show the payload directly from the landing page. For simplification purposes, I did that here. And what the XSS is doing, it's logging out that it's starting, and it's going to be hitting a fetch later log endpoint. And we are running 12 requests every 2 seconds. And activate after is the interesting part. We are activating that FetchLater request after a specific amount of timeout. So 2000, 4000, 6000, 8000, etc. until the 12 times that one. Once it has been registering all the fetch laters, and after 10 seconds, we are going to logging out from the session. When you are logging in as a victim, we're just displaying normal user, and we are sending our payload with the username directly there and allowing for a logout. That is the WebSocket trigger so that the WebSocket knows when the specific username has been logged in. What's happening for the fetch later log? That's basically our canary callback to verify that we have achieved exfiltration or calling specific internal endpoint that will give us the tokens or change the password. What we are grabbing from this fetch log, we are giving the session ID, the current user, when it has been done, and we are broadcasting that to the WebSocket so that we have a better idea what's happening. The logout is killing the session ID and the username cookie. And as you could see also in the fetch later log, I'm grabbing the username from the cookie and also displaying the cookies in there. So what is doing the exploit? The exploit itself is pretty straightforward. There is some styling first, but we are going to open a new tab and log in as an attacker account. The XSS payload will trigger all the registering of the fetch laters request, and the session will be tracking the cookies and who's sending and what. The XSS itself, after 10 seconds, will logs out the attacker account, and we will then initiate a victim login in a new tab, and we will just verify that the fetch later requests are continuing with this time the victim session context instead of having the attacker one. So if we look at the caddy file, we can see that the attack server will be hosted on 8444, and we have our exploit there. So when we open our page, we are welcome with this one. And you should keep a look at the tabs on the right. We are going to start. What's happening is that we have the attacker login phase, which is going to set up the hello attacker. And if you look at what's happening here, we have fetch laters, which is called, and it's called under scheduled by attacker. It's running under attacker and has the cookies for 4D7. Once we're logged out, it's going to be anonymous. And once we log in the victim, all of them which were anonymous are now running under the current user, but they're still running and they are still the fetch laters requests that have been scheduled by the attacker on the first XSS, which means that we are able to exfiltrate data from the victim session. That is where Slonser blog post finishes, but Rhino Raider from Critical Thinking podcast have also suggested to leverage redirect loops in order to extend the lifetime of this background request. More precisely, that's because this trick here has a timeout limit, but if you mix that with redirect loops, which on Chrome allows you to go over 300 seconds, you can then loop it a specific amount of time. So by mixing the redirect loops, like I think it's 20 max in the chain, and the waiting before redirecting for up to 5 minutes, you can chain a lot of time before getting the call back to the background request. And so to illustrate that, I made a lab 6, which is going to pretty much do the same flow. So the same things. However, this time our XSS is a bit different. So we are going to activate the self-XSS after 2 seconds, and we are going to an attacker server in the endpoint start. And that one is going to be posting all the information we need. And once it's done, it's going to be logging out the attacker like earlier. And the new thing is that this start is going to start the redirect chain. And the start endpoint is redirecting to the redirect with a step number ID on the path. It's going to be a 307, which means that post will be sent as post. And we are going to wait for the specific amount of time that we have set and redirect it as we have set it up to be redirecting. So as long as we are below the 5 redirect chain here, we are going to redirect and keep track of the step. Once we are done, we're going for our target URL. In this case, we have set 5 redirect in the loop, wait for 5 seconds, and fetch later log. It's going to be a target URL for our XSS. So resuming a bit the idea of the attack vector earlier, which will be exfiltrating or doing some privilege escalation thing. If we go for start exploit, we can see that as earlier, we are starting the attacker endpoint. However, we have only one fetch later request and 5 redirect loop. So you can see here that we have those redirect loop that are done while we are logged out of the user attacker and have the victim logged in back. And if we scroll down, the fetch later, once it has resolved all the redirections and finally go to the target, it's doing it under the victim context, although it has been scheduled by the attacker 2 seconds after the first success. So this cookie here is the victim's cookie and not the attacker's cookie. Here we go. The labs are going to be on Slonser, Self-XSS labs on my repo. Thank you everyone. Take care. Bye bye.